welcome everybody. It's good. I can't say to see you again, but to have you back, just to properly say hi to everybody. Where's my picture? There you are. So, hello. I hope you enjoyed the previous sessions, and I trust that tonight will be a good session for you as well. I hope that you learned something, and let's take it on. And to save the bandwidth, let me switch off this camera again. Let's start. Just for a reminder, for those of you that joined the first time, I'm not sure if there are any, if everybody, if all of you repeat, but let me confirm, this is where are we now? Part 4 of this 8-part series.
Yeah, there's 2 new people on, Herman. There are 2 new people in the evening. Yes, it seems that there's 2 new people.
Okay, welcome to you as well. Well, especially. In any case, let's move on. This is part 4 of an 8-part series, and one of the main purpose of this series is to try and make the standards more understandable. I mean, if it's understandable, if you understand the principles behind it, know what it's all about, it's easier to read the book and to apply the rules in the standard. It is important just to note again, let me remind you, the whole lecture is in English. You must have at least a basic understanding of plumbing, and I do expect that you should at least have some basic physics understanding. Otherwise, some of the principles might be a little bit challenging, but it's really very simple stuff. And then, as far as questions go, throughout there will be a spot at the end of this session to ask questions. You're welcome to save up until then, but at any spot in between, please ask questions. And then Lee, especially for you, feel free to interfere at any stage you want, to interject as you normally do.
You can count on me.
I'm sure. Okay. A quick recap on what we discussed last time. During the last session, we firstly discussed the basics of certification, and the essence of the message was, how do you as a plumber know that a component are certified, that a component comply with the requirements, so that you can use that. The second topic that we've discussed was a basic overview of Office piezo installation system, the various components that we use, and so on. And what is quite important to understand in that we've discussed in detail is the fact that it's a system with multiple components, and they all work together to achieve the same thing. We also discussed warranties, the legal side of that, and the effect, what happens if you happen to make a warranty to lapse, the realities. And then again, especially Lee, this one I added specially for you. Ask the question. And I think that was one of the most important things that we discussed. Ask the question. Don't assume that a product complies. Don't assume that something is correct. Ask and get the actual evidence. So, what are we going to discuss tonight? We already said we talk about vacuum breakers. Very interesting subject. Now, a quick overview of our session tonight is, first of all, we look at the purpose of a vacuum breaker. Why do we have it in the system? How does it work? I'm going to give you a basic overview, some insight into the requirements that a vacuum breaker has to comply with. We're going to talk about where it fits into the system, and then a quick conclusion. And again, the real thing. If you walk away from the session tonight, what should you walk away with? You should understand the importance and the working of a vacuum breaker, so that it can be installed to work effectively. I have seen various installations, various areas where it was clearly quite difficult, space constraints, all sorts of things that make it difficult to install the system as the book says. But and then I've seen areas where the vacuum breakers have been used incorrectly. And if you don't understand how it works, you might be inclined to think that, oh no, it doesn't matter how I install it as long as it's there. it can actually play a difference and make it not to function correctly. Now, let me ask a question straight away. Think about it. Why? Why is there a vacuum breaker in the system? What is the actual purpose of the vacuum breaker? And I'm sure you will enjoy the next picture. And I think that clearly, that's about the best way to explain the big reason for a vacuum breaker in the system. It is to prevent contamination of drinking water, to prevent contamination of potable water. I mean, that's part of one of the critical things of a plumbing system. Why plumbing is such a critical trade as well, is to ensure that there's clean water, clean, hygienic, healthy water available. And contamination must be avoided at all costs. But you might ask the question, what does clean water have to do with a vacuum breaker? How does a vacuum breaker come into the picture? Now, again, vacuum breaker, one of the components in a system. There's a number of components that with the same aim, but the function of the vacuum breaker as a component in the system is what we will be discussing. Okay, so let's first look at some physics principles. What makes water flow from one side to another side? What makes it flow in a specific direction? Water always flows from a high pressure to a low pressure. Now, we've discussed in the previous sessions energy, balance of energy, making sure, or conservation of energy, that the total amount of energy between 2 points are the same, but you can transfer or change the type of energy. And there's various things that can cause a pressure difference, but it is only the pressure difference that drives the water from the one point to the other point. For instance, water will flow uphill if the pressure at the bottom is higher than the pressure at the top. Okay, this is a simple principle, and I'm sure everybody understood this already. But it's important to just recap, remember that, so that we can get into the understanding of the vacuum breaker, where it fits into the picture. Similarly, let's look at another principle that I'm sure everybody is quite familiar with. A quick reminder, reminder of it, siphonage. Having to drain water from one vessel to another. And again, I believe the image is clear enough, easy enough to understand. The one question is, what makes the water flow? What causes the water to continue flowing in this scenario? The pressure at the top, where the laser point is showing, let me see if everybody's screens are updated. The pressure at the top is therefore higher than the pressure at the bottom. And that is why I even included the formula. The pressure equals the density of the liquid, of water, times gravity times the height. So the higher the height, the bigger the pressure difference. So there's a pressure difference. Air pressure, there's ambient pressure on the top, which forces the water down. But especially this area, where the height between the top level and the bottom of this pipe, that height causes, you can call it suction. It pulls on this pipe, and that gravity pulls the water out. And because it pulls out on the bottom, I mean, the water has to fall because it's heavier. There's a pressure difference. The pressure is low at the bottom. It will suck up some of the water in the pipe because the top end is inside the water, and this process will continue to happen. Now again, it's quite simple. What does this have to do with a vacuum breaker? Why are we looking at that? And forgive me, but I just need to, oh no. Okay. Can you still hear me, everybody? Oh, there it's going. Sorry, my computer froze for a while, but it seemed to be going again. Okay.
Yeah, everything is fine on our side. 100%.
Okay.
No problem.
Yeah, now it's running again. Good. Now, let's get back to the example. Let's try to make the principle practical here. On the image that you see now, show a main water supply, the municipal supply, with two lines, one to a tap, and it's somebody filling the swimming pool. I'm sure it's not on Gauteng where all the water restrictions are, but that swimming pool is being filled. At the bottom we have a house, and the house is supplied with water. So the yellow arrows indicate the direction of flow. Because there's a higher pressure in the supply line, the water will flow towards to the taps, to the areas where the water is used. Now, what happens if there is a leak suddenly in this supply line? Water on the municipal line now suddenly starts leaking and it runs out. What effect will this have on this complete system? Because as we've explained previously, there must always be a balance of energy. Energy cannot disappear. So now suddenly you have water running out of the line. There's a velocity. It causes a drop in the pressure. Let me just get that image up, and that explains it. It causes a pressure drop at the point where the water leak, which means now water will flow in that direction. It means water out of the household might flow towards the leak. Water in the main line might flow that. But you also have the siphonage out of the swimming pool. Because the tap remains open, the hose is still in the pool, that water will be sucked up and it will be fed into this line. And the question is it really a problem? Why do we care about that? The question then is, as shown on the next slide, now the water mains, now somebody came, they fixed the leak got fixed, and the water pressure returns. What happens to that? You might notice in the previous slide the yellow arrows denoted clean water, and the red arrows, let me show that again, it was the red arrows shows the dirty water, the swimming pool water being siphoned back out of the swimming pool into the line. In the next slide you can see that dirty water, now that the pressure came back, is now flowing in the same direction that water would have flown. But there's a strong possibility that water would now be flushed back into the household. It gets flushed down the line, down the municipal supply line. And that, I don't have to say that, but I think that's a clear example of contamination, of a potential health hazard. Now, yes, we can argue swimming pool water, what other types of contamination could happen. And we need to understand that in a plumbing system, this caters for not only for the day that everything goes well, but it does cater for the day that things might not be as usual. You don't know who's been doing what. Where did somebody put a hose, for instance, into a washing machine full of washing liquid? Or what other liquids could have contaminated with the water. This is a simple example of one thing that can happen. But in reality, you always need to make sure that water flow only in the direction intended. If water can only flow in the direction intended, you can make sure that no unwanted water is siphoned back into the system. Only clean water will come out the pipes. Okay, if we now go back to our earlier example of siphonage. How do we stop? If we look at this example, we have the water flowing. So how do we stop this water? How do we make it stop flowing? Prevent, aiding the help of preventing that. By cutting the line, it's a typical example. If you cut that tube at a level higher than the top level, then the loss of the water will run out, it will suck air, and there's no more height. You see the formula says the pressure is now equal to 0 because there's no more height difference between the top and the bottom. The pressure is 0, so there's nothing driving the water out the bottom again anymore. And Similarly, if we look at our example with the swimming pool water, to prevent the contaminated water from filling the pipes, how do we stop that? And you use exactly the same principle. You cut the line. In other words, by cutting the line, you allow air up, or air to be sucked into the line, and it will settle at the lowest point, at the point where the leak was, because there's nothing that drives it further. And that is much safer than how to say, it's much safer than having the dirty water inside the line. And this is exactly the principle that the vacuum breaker uses. It uses a principle of allowing air at the right conditions. In other words, when air shouldn't be in the line, it won't be in the line. It will, the pressures, the plumbing system will be sealed. But when the conditions are right, when conditions try to force water to run in the wrong direction, for instance, and could potentially cause contamination, it would rather allow air into the line, preventing any siphonage or any movement in the wrong direction. And in that way, keep the line safe. So as soon as the pressure comes back, it fills the air gap, and you have clean, fresh water again. Now, a second practical function of the vacuum breaker as well is not only to keep the water clean, but it's also to protect the geyser, to make sure that the geyser never runs dry, that there's always water in the geyser, so that the element won't burn and so on. So if you look at the image that's on the screen now, and I think it's on most people's screens, then you will notice in the example of the installation that we've shown, you can see the vacuum breaker at the height, and it will allow water down to the red line. In other words, the water will fall, and it will reach that level, but there's no more water in the line to allow water to drain any further than that point. And for that reason, the geyser cannot be or cannot run dry. So the only way to get the water flowing through the geyser again is to get the pressure up, to force pressure again from the inside through the geyser, and to fill the tubes up to the vacuum breaker again. Now let's quickly, before we talk about the function, how our vacuum breaker function, let's quickly put up a quick poll. If you're ready with that on your side, Lee.
Yep, got it there. So for the new guys, so guys, here you go. Great. So you want to talk to that, Herman?
Okay, yes, let me explain that. I'm just opening on my side the screen so I can also see what you see. Okay, the question is, what is the maximum vacuum that can be generated? Is it 200 kPa, 100 kPa, 85 kPa, 50 kPa, or unlimited? If you look at it I assume everybody understands that. To put it in perspective, what's the typical, you all know the pressures that plumbing systems run at. Okay, let's see what you think. So make your choice. 200, 100, 85, 50. And remember, the question is the maximum. Forget about a plumbing system. In life, anywhere you go, what is the maximum vacuum that can exist? Or are there no limit to that?
Okay, Herman. My polls went closed there. We've got 71% people voted, right? So I'm going to close the poll now. There's a few more votes in, guys. Just put your, there we go, great. It's not a, okay, great. So I'm going to close the poll now, right? And let's see. As they say, it's a unanimous answer.
It's a unanimous answer, you say, and it is very, very, very interesting answer, which I might add is absolutely wrong. There is a limit to the maximum vacuum that can be pulled, and the question is what is vacuum? Let's look at that. Sorry for the moment of silence. Okay, if you look at that graph, trying to explain, see pressure does have an absolute minimum point. If you look on the left-hand scale, it shows ambient pressure. In other words, in Pretoria, Gauteng, our atmospheric pressure is about 86 kPa, I would say, which is on that side, where the laser pointer shows now. At sea level, at coastal level, the ambient pressure, we know pressure is higher, it's about 100 kPa. Now vacuum is the difference between the ambient pressure and the absolute zero. I mean, absolute zero means the air molecules, can I say, they're so far apart, they don't apply pressure on the environment around them anymore. So look at the example on the left-hand side. At coastal level, where the ambient pressure is 100 kPa, if you reduce that, if you go below that, 25 kPa below that, you have a vacuum of 25 kPa, 25 kilopascals, is the vacuum that you have drawn. This is where you refer to gauge pressure. You might have heard people referring to gauge pressure versus absolute pressure. Absolute pressure in this case says the ambient pressure is 100 kPa, but the gauge pressure at that point only is 0 kPa because there's no difference. At this point, it means the gauge pressure is minus 25 kPa. It is a minus because it's from the 100 kPa going downwards, which means that the maximum vacuum you can pull at coastal level is 100 kPa, for instance. In Pretoria, Johannesburg area, the maximum vacuum is approximately 86 kPa. Now, it's not very important to know and to remember all of these values, but I do believe it's relatively important to just understand the principle of what the vacuum really is. If we now look at the vacuum breaker, how does it look on the inside, and what is the function of it? How does it work? The vacuum breaker has got a body, the brown section. Okay, you can see that has everything. You've got the gray cap that covers the top of the section, and then on the inside you see the gray disc. It is like a orifice, a plate, a seal that is kept in place by means of a spring that pushes it in place. So normally, under normal conditions, this is what a vacuum breaker looks like. It's got the seal that's kept in place with a spring, and the more water pressure you have, the tighter it pushes against the sealing surface. So no air can escape, your water pressure is safe, everything goes fine. But what happens now if the water pressure reduces? In other words, you now have a loss of pressure on your inlet line. Somebody opens the tap on the outlet side, and suddenly it is gravity that tries to suck the water out. It can't be fed from the supply line because there's no more pressure. The only pressure is generated by the height in the water. So what happens? The pressure turns around. So this pressure, like the thermosiphoning that we showed, creates a negative pressure, it needs to move down. It overcomes the spring, plus you have the air pressure coming from the top that pushes down onto this disc. And as soon as the air pressure is higher than the suction of the water, it will allow air. You see how the air comes into the system. And the more it sucks, the more air will come into the system, and that allows the pipe to fill with air from the top downwards. I trust, you see, it's interesting because I can't see everybody's faces. I just assume this made perfect sense and everybody's happy with the explanation.
Herman,
yes,
just to add to that specific one, This is what we refer. I don't know if you touch on it a little bit later, so I might be a little bit premature with you. This is what we refer to as a single jumper, right? And the PB1s, I think it's the PB1s, the Cobra's PB1s. I didn't. Is that they have a double jumper, and that's why those ones are much more expensive. Is because they've actually got two seals in it. So if one fails, because as we know, the failure of vacuum breakers are pretty common out there. Right, and this the more expensive vacuum breakers actually have double jumpers in them and not just single ones. So I just thought I'll just point that out as a useless fact for the audience.
Okay, thank you very much for the useless fact. In general, you will notice that I try not to make reference to any specific brand names, and the most important thing is
yes,
I
knew when I opened my mouth and said that.
That's fine. But I think I think having said that, it's a very important thing to notice. It's not about the brand. It is that different suppliers, different brands can offer different solutions. The principle remains the same. But I mean, that allows you, now that you understand, you can interact with the various suppliers and say, you claim this product is better than the rest. Why? Show me why. Tell me why it is better. And understanding the jumper thing, you can say, oh, now it makes sense. It might be worth having the one with the double things to ensure that it will always work, and that when one fails, the next one is still in place.
Yeah, the audience is supporting me, Herman. They're saying, thank you very much for that information.
Okay, good.
I can give you some more useless information if you want. But I'll go shut up now.
Okay. Good. So we're moving on to the next part. In this part of the session, the slides, I'm going to quickly touch on some of the requirements that the vacuum breaker need to comply with. Now I know, please. I know the picture, it's not a vacuum breaker. I'm not trying to show you a vacuum breaker in the picture. I'm trying to show you the mark in the little circle. We get to that one. Now, some of the requirements of a vacuum breaker that gets tested when this thing is sent to a test facility or to SABS for testing. Some the requirements is material is one of the key components. Generally, DZR brass is allowed, stainless steel and plastics, various types of plastics. And understand when a plastic is allowed, the standards doesn't say you may use plastic for the product. It says if it's plastic, and it gives a whole set of tests that needs to be done to verify that the plastic can handle the different temperatures, that the functionality remain intact. Similarly, stainless steel, it will provide you the type of stainless steel that is allowed, that is regarded as good enough for the plumbing systems. And DZR brass. Not only brass, it must be brass that is resistant to dezinctification. I mean, this is a topic that we can have more than one session on its own, and it's extremely important in our overall plumbing system that the right type of brass is used. Because if you do not do that, this is typically where a fitting that's plastered inside a wall starts leaking after 2-3 years, and it causes enormous amount of damage and expensive damage. But how do you know if it's the correct brass? Other than looking for the SABS mark on the product. There's one of the requirements says this component must have the DR, must be marked DR. It must have that mark on. So that's what I'm showing in these images, the mark, the DR mark. And if you get any component, not only vacuum breakers, all plumbing components, brass components must have that on, and you must be able to see that. So if you get somebody claims that their product is SABS approved or that it complies to the requirements, and it's a brass product and you don't see that mark, it should bring up a red light to say, whoa, this can't be. It's something is out of place, because it has to be there and it's in all the requirements that it must be there. Then we look at connections. Something similar, we take it for granted. Whatever you pick off the shelf will fit. It will fit your plumbing size. But there are some detailed requirements in the standard addressing the specific sizes that it needs to comply with, so that it's a standard sizes that will work. The one thing that I want to just draw your attention to, and again, you don't have to remember all the numbers of the SANS standards, but notice that for compression fittings, there's a standard 1067 part 1. There's a full standard that explains all the requirements for these for a compression type fittings, and it's a book on its own. It's a whole process. It's not just a quick check to see if it's 15 mil or 30 mil and it slips nicely over the pipe. Similarly with threads, if it's a threaded connection, SANS 1109, there's a in-depth analysis that needs to be done on a thread to confirm that it complies with all of that. And that's all aspects, quality aspects that happens behind the scenes that you don't know about. You don't really need to know about it, as long as you make sure the product complies to the national standard, that it's certified. Then you know you're safe. It is that, and all of these checks have been done. Another part of the requirements is the pressure rating, that vacuum breakers as well also carry the pressure rating, and they come in all the different sizes. Now that doesn't mean that you're going to get stock of all of the vacuum breakers in all of these pressure ratings. These are the ratings that's allowed in the standard. I think the more common ones is the red and the green, or let me be correct, the flag red and the brilliant green colored indicate the correct pressure. And you will notice, we'll touch on that at, I think it's session number 7, where we look at the plumbing layouts as well, is the correct fittings must be used, or the fittings throughout the system must have matching pressure ratings to ensure that it will actually function correctly, that even the vacuum features of the vacuum breaker will still work in a 600 kPa system. Or let me simplify that. It is depending on the brand and the product, it is possible that a system or a vacuum breaker designed for 600 kPa might not function exactly the same when it is fitted on a 400 kPa system, or the other way around. So just bear that in mind when you select the vacuum breaker to use for the system. Then the last, let's look at the performance requirements of a vacuum breaker. The tests that's done on the vacuum breaker include not only the start to open pressure, in other words, go through a process where we measure exactly at what pressure or at what vacuum does the pressure or does the vacuum breaker start to open. And that is, it has to open at 3 kPa, which is 300 millimeter water column. Now, that 300 millimeter water column must be very familiar with to you. It should ring a bell already somewhere along the line. Now I've lost my own place. Okay, sorry. We've mentioned that. So the start to open pressure, that is always verified. Then it is also important that the vacuum breaker can allow air at a fast enough rate into the system, that it doesn't only open and then not allow enough air to actually function correctly, because if it's too much of a restriction and it can't allow air in fast enough, it could cause a situation where water is actually drawn out of the geyser, or some siphonage can come back into the system because the water can't come out fast enough. And for that reason, a vacuum breaker is also tested. It goes through a whole process of increasing the vacuum, and continuously measuring the flow rate, or the vacuum flow rate, through the system. And there's actually a whole series of requirements around that in the standard, but it ends in a point where it says at a 9 kPa, or a 9 kPa vacuum, which is minus 9 kPa gauge pressure, the flow rate of at least 100 liters per minute must be achieved. 100 liters per minute of air must be achieved through the vacuum breaker. And then endurance. Endurance is always an important thing. It is to put the vacuum breaker through its paces. Let it suck air, close. Draw a vacuum, close. Draw a vacuum, close. For I cannot recall the number of cycles, but it's quite a large number of cycles. So again, if it's been through the standard, if it's been tested, it will function for a long time in the system. Now at this stage, I want to repeat the fact that a vacuum breaker is one component in an overall system. If you fail to install the correct vacuum breaker, or if you fail to install it correctly, it can cause the product not to work, which means where there previously were 2 or 3 maybe safety checks before something can really go wrong. If you haven't installed it correctly, you take away one of the safety checks and you make it 50 or 30% more likely that if something else goes wrong, that it will have a negative effect on the overall installation and could cause contamination. Where does the vacuum breaker? Hello,
Herman. Richard has put in a question. Martin has also put in a question, but I'll answer that a little bit later, Martin, because I think we're going to address it as we go along throughout the session. But Richard, I don't understand your question too well, so I'm just going to actually bring you on so you can actually ask the question to Herman. So I'm going to.
My name is Herman.
Yes, to Herman. Sorry. So Richard, I've unmiked you, so just ask your question.
Hi, can you hear me?
Yep, we can hear you. Far away.
Okay.
I can hear you.
Hi, good evening, Herman. Hi, Lee. My question was regarding the pressure rating of vacuum breakers. I'm not aware of vacuum breakers that are rated for a minimum pressure, let's say 400 kPa, that cannot be used in a 600 kPa system, for example. I would have thought that because they are units that are not responsible for regulating or relieving any kind of pressure, like a TP or a PRV, that their positive pressure rating would be a threshold predetermined, you know. So it's like, I know most taps and fittings and those sorts of things are tested to 2,000 kPa as a minimum benchmark. Does that not apply, not necessarily to 2,000 kPa, but does that not apply to vacuum breakers as well? Or are there in fact vacuum breakers that are only rated for, let's say, 400 kPa positive pressure systems?
That's a good question. I know. Okay, I cannot tell you what is available in the industry. I think some of the other people might be more aware of the different types that's available. What I can confirm is that from a standards point of view, various pressure ratings is available and could be allowed. And the standards, if you look at the installation standards, it actually has specific requirements to say that the vacuum breaker must be matched to all the other components that is used in the system. So when you do installation, it's a 400 kPa installation. All the components must be 400 kPa. As far as I recall, it is only the geyser that is then allowed to be of a higher pressure rating and not a lower pressure rating. And similarly, if you then do a 600 kPa installation, all the components must be 600 kPa. And the same obviously applies for the lower pressures, which is not very common.
Am I still on? Can I interject? Okay. Herman, I want to put it a different way. I'm looking at a vacuum breaker because of the fact that it comes into play when we've got negative pressure situations. So I look at a vacuum breaker in a status quo system, in a system that sort of is doing its job. I look at it in the same light as you would a T-piece, a Konex T-piece. It fulfills the same function. Or put it this way, a cap or a stop end on a pipe, which effectively it fulfills the same function. So I would question whether or not a cap on a pipe, for example, would need to be rated at 400 kPa. Let's put it that way. Which it wouldn't. It would certainly be rated a lot higher than that. We're talking positive pressure. It's
Okay,
just,
now,
it doesn't really matter. It's not, yeah, it doesn't really matter, but it's just a query that I had.
okay, I understand your query, and it brings up interesting questions, because if you look at it on face value, and I think most common design, especially if you look at the image that I've shown, it would typically, I would tend to agree with you. Say, in other words, if it can handle 600 kPa, then 400 or 300 or 200 shouldn't be a problem either. The question is that all designs are not necessarily the same. There might be other things that affect that. For instance, the balance between the spring that push upwards to keep it in a closed position, and the combination of the water pressure. They might need to use a different spring pressure or things like that in order to maintain that. But then, as you rightly says, when everything is there, when it's under pressure, you shouldn't really notice much of a difference. But if they had to use different components in some different configurations, as Lee indicated, you do get various different configurations of vacuum breakers. If the components had to be adjusted to make it work at the higher pressures, it might also have an effect on the start to open pressure, for instance. And that's important to notice, that the start to open pressure, that 3 kPa, is a very, very, very low pressure. It is a very it can take fine tuning to make it actually work at that pressure without failing. And I think that's where the risks come in. Again, from a technical side, technically I believe it's quite possible to design something that will be able to withstand all pressures up to 600 kPa or even higher, and still work well. But it's not a guarantee that all designs will work like that. And from that point, I can only refer back to the standards and say, well, let's look at the rules. And from the way I understand the rules, it says vacuum breaker, you have to match it to the rest of the system.
Thanks,
Okay.
Herman.
That answers the question.
Yeah.
Okay.
I think.
Yeah, thanks, man.
Okay, great. Let's move on then. Okay, Herman, back to you.
Okay. Then, as you can see on the picture, I don't have to go much further than that, but it's interesting to note that the start to open pressure is 300 millimeters water column, and the standard actually requires a vacuum breaker to be installed 300 millimeters above the fitting. I also want to note at this stage is don't only look at 10254, the standard for geyser installations. Also look at 10252 part 1. In other words, the parent standard for all installations. There are some of the requirements that's captured in that standard, which is not necessarily in 10254, and everything needs to be complied with. Lee, can you bring up the next poll? Maybe first ask the people if they're ready to continue.
Yeah, I think before we start.
Sorry to keep interfering. There's only about 3 slides after this one.
Yes. No, I think we're making good time, even though we started late. I think you know, when you started off the series, Herman, you said to the guys that, you know, as we go through the series, you know, it's not, we're going to get across things, and we're going to explain why they are like that. So, for instance, this 300 millimeter, you know, everybody knows it's got to be 300 millimeters. But the question is, why must it be 300 millimeters? And here it is, guys. Here it explains to you and says that a vacuum breaker needs a certain amount of air to open up that spring, right? And therefore, that amount of air, as Herman says, is 0.3 kPa. And that is why it's on a 300 millimeter riser. Some manufacturers, and you know this useless bit of information as well, go and ask your manufacturer who produces the vacuum breakers, and go and ask them, at what vacuum does your vacuum breaker open up? And I can tell you there are even some on the market that are so fine-tuned that they are able to open up at 0.1 kPa of pressure. But that's a bit more useless information.
Thank you for that extra useless information.
Yes.
I think it was valuable.
So what did we learn from this session, or this my statement now? Ask the question, guys. Anyway, I'll bring up the next poll, Herman.
Thank you very much. And the next poll is a very difficult one. You have two possible answers. If a geyser is on the ground floor level and there's a tap on the first floor level, where should the vacuum breakers be? In other words, I've seen installations like this. For some reason, it sometimes happens. Geyser is on the outside the building, on the ground level, but it feeds 2 stories. Where does the vacuum breakers go? As the picture shows, on top of the just on top of the geyser, or at a higher spot, higher than the taps on the second floor.
Great. So guys, throw your votes in. There we go. We're up to 50% response. Good. This is a very interesting one, guys. Very, very interesting one. Okay, great. Let's leave it a couple of more seconds. We've got 86% of the vote. Stick it in, guys. Come. What's the worst that can happen? You can get it wrong, but it's a learning curve. Okay, great. So I'm going to close the polls now, Herman.
Yes, and let's see what happened.
And let's go and see what happens.
Above the geyser as usual. Shoo. I anticipated sort of a 50-50 answer on that one. And 8%. How many people, how many guys voted?
8%.
Number 2, 8% of them. How many
Yes.
people are that? Okay. And in this case, the minority is correct. If you look, if you look at the stat, yes.
You know what I suggest to answer this specific one, Herman? You had a, yeah, okay, you've got a slide. Yeah, I do apologize. Your pool one explained it quite nicely. You know, your pool picture.
Yes.
Drained out.
That
one. But anyway, I see you got one. Yeah, so I do apologize.
At least I've used the same tap as in the pool
Yes.
the pool one. So I hope everybody would notice that one.
Good.
But this is exactly that. I don't have fancy images to explain that, but the reality is, and again, don't pay too much attention to the actual plumbing layout. It's explaining the principle. The standard, again, look at SANS 10252 Part 1, Clause 6.3.3.1. That's a reference, the rule that says there must always be a vacuum breaker at least 300 millimeters above the fitting outlet or 150 millimeters above the overflow level. Now, we don't have to go in too much detail about what level is what level. At the moment, overflow level typically in a toilet is where will the water overflow. But, okay, that's not the important part for now. The reality is, it is a requirement from the standard. Why does the standard require that? As Lee said, imagine now our pool image fitted to this tap again. If there's water, a practical example, on the second floor, somebody's been doing washing in a top loader washing machine, for instance. There might be a pipe connected to the tap onto the top loader washing machine. The tap is open, and something goes wrong. It is quite possible that water gets sucked out of that top loader through the tap down the bottom, except if there's a vacuum breaker fitted in the right position, 300 millimeters above that. Then the water will take the easier route, drain the air through the pipes, and you won't have that. The safest way is to have the vacuum breaker at the bottom as well. So you don't have to leave the vacuum breaker at the bottom, but this becomes a bit more interesting if you go through the standard. It explains various scenarios on when the vacuum breaker goes in which position. But if you ever in doubt, put it in both positions. Now my last image came up too late. You can just look at the little man that's sitting on the arrow, because that was supposed to be my prompt to ask to explain to you why it is necessary to install it there.
Yeah.
Good.
You know the answer to this, Herman, it was quite interesting. The response to this specific thing is that where the guy said 92% said at the geyser. And it's quite interesting. Why? Is because we've never asked the question, why must we put it here? Why must we not, why do we put it here? Martin has asked a question, and I want to just quickly jump in at this particular point with his question. He asked, and he said, why are 2 vacuum breakers required? We understand it on the cold water side very easily because it prevents the siphoning out and a few other reasons. But why on the hot water side? This slide explains it, Mota. It explains to you why you need it on the hot water side. Because if Herman said there, is that if you look at this tap, and if this tap was in a washing machine pipe or whatever it is, and the geyser got sucked out with hot water or with the water, and there was no vacuum breakers, this water would be sucked all the way into the geyser and down the pipe outside into the main water supply. And as Herman showed you in the beginning, you have a dirty amount of contamination into the water supply. So that's one of the main reasons why we do that.
And also on top of that, just bear in mind a plumbing system is not intended to have one protection. It's intended to have multiple protections. It's something you can work out statistically. What's the chance of something going wrong? Remember, a plumbing system going bad kill people, or it can potentially kill people. It's that serious. So you don't just add one safety feature. When in doubt, add extra. Make double sure that nothing can go wrong.
Yeah.
So don't think, but I've already fitted this one. The other one's not going to make a difference.
Okay.
It needs multiple protection.
100%, guys. I mean, Herman's 100% in what he's saying there. And Henry, he says, yeah, I've never seen an install like this over all my years as a plumber. And you know why you haven't seen it like that? Is because 90% of the time, the highest point in the house is the geyser. Isn't that so? So therefore, your vacuum breakers are always become on the highest point on your system. And that's why you generally not see it. And other than that, Henry, have you ever actually heard about the standard where 10254, where it says it has to be above 150 millimeter on your highest point? So this is the first time you've been made aware of it. And because most of the plumbers are not aware about it, they don't do that installation like that.
Yeah, I can add to that. I think in one of the earlier sessions where we spoke about standards and so on, we've said why is the standard there? It's easy enough now to say, well, the standard says so. We should have followed that. I mean, the standard is there to protect your blind spot. I've learned the hard way that if you don't pay attention to all the requirements, you might miss stuff that you never thought about, that you didn't think was important. So don't ever leave something that's in a standard just because you don't understand why it's there. There's a reason for it to be there. Maintain that. What we're trying to do in this course is to try and sort of help you understand it a little bit better.
Correct.
Okay. So, in conclusion, vacuum breakers are important components in the chain of safety components. They must always be fitted where they will protect the whole system, not only a portion. And I think that to me is remains one of the key things. The vacuum breaker is not there to protect the geyser only. It is actually almost more important to prevent contaminated water from entering a system at some weird situation that you just never anticipated is going to happen.
Yeah, vent your systems as much as you can, guys. Switch it off. As Herman indicated on the previous slide, put as many safety measures in as possible. You can never be over it. So vent as much as you can.
Great. So that brought us to the end of this session. Are there any additional questions? Anything else you'd like us to explain?
Yes, 100%. Ryan just put a comment through here, and I thought it was quite nice. He's gonna sound very smart tomorrow. but Ryan did also. I'm glad. He also asked a very, very interesting question. He said that could a non-return valve? Now you see, Ryan. Now we're thinking. Now we're thinking. We say, could a non-return valve not be used instead of a vacuum breaker on the second floor?
Very, very interesting question, and that is actually addressed in the standards, SANS 10252 Part 1. does elaborate on that, where non-return valves can be used and cannot be used. And the short answer to your question is no, it cannot be used. The standard says you shall have a vacuum breaker, so you cannot replace it with a vacuum breaker. But non-return valves can be a very, very powerful ally in your whole process to prevent backflow in systems and to prevent water from flowing in the wrong directions. But at no stage may you replace that, may you leave out the vacuum breaker and say, oh no, I'd rather use a non-return valve.
Yes. It was interesting that you made that comment, Ryan, because we were looking at some, the operations manager for IOPSA, he sent some pictures around last week. And it was a geyser installation in Australia, and their standards, the way in which they install the thing, and they don't have vacuum breakers. They actually have a non-return valve on the cold water side. That's how they do their installations. Now, Herman says, God, technically, it is sound that you can put a non-return valve in, because then you won't have any flow out of your geyser. However, sorry to say, guys, the standard says you've got to have a vacuum breaker in the system. So, unfortunately, it sits like that.
Yeah,
okay.
I think I just want to add to that. Remember, vacuum breakers aren't always as nice as we think they are.
Yes.
They wear faster than other products. The rate of failure could be higher depending on the type of vacuum breaker you use. So standards also acknowledges the long-term endurance of products. And I'm not going to act as if I really know where all of the requirements come from, but I have learned over time to trust what's in the standard. Sometimes I also only learn long time later on why the standard always been there that I thought was a over the top requirement.
Okay.
So I've learned to trust the requirements.
Yeah. Okay. So there's just a few more. Colin actually asked a question, but he's just gone offline now, and we lost him. But he'll pick it up on the recording. It was. Okay. He says, "What if the geyser is against the roof and there's no space for vacuum breakers? What do you do?" And if you know that one, Adrian.
You make space.
So what you do is there is a if you read the standard, it says that you can cut directly in the line, provided you are 700 millimeters away from the outlet. So you can run it level with the top of the geyser as long as it's got a 700 millimeters.
That is okay. That is correct. Thank you, Lee.
And if you speak to one of the manufacturers who have got a very light vacuum breaker jumper, they'll tell you a different story. So I want you guys to go and find out that one, who that manufacturer is. Then going on with that specific one is that Colin did also quickly ask, and it's not necessarily for this question. He says, he talks about, so can I put a 400 kPa control valve into a 400 kPa system? Yes, he can do that, because the standard says the must be equal, provided it is less. Is it less? Is that the right thing? It's provided the valves are less than the pressure rating of the geyser. All the valves in the system. So
yes, the geyser must always have the highest pressure rating.
The highest pressure rating.
The geyser must have the highest pressure rating of all the components. The same as the rest or higher.
Yeah, but Herman will be touching
on all of
the
other components.
He'll be touching on in the pressure one next week, most likely. Hey, it is next week.
Most likely, yes.
Yeah, pressure control. That's the third week after next. The safety valves next week, which is also important. Then the last one is Henry again's asking he fails to see why the hot water why there should be a vacuum breaker on the hot water slide. So could you possibly just go back to that slide again, Herman? It's the 2 slides back, and just do me a favor. That one. Do me a favor. Bring up your
slide. Yes.
Yeah, just bring out your pencil, your little drawing thingy, and just draw on there a pipe lying in a bath or something, so Henry can see that. While Herman is doing that, Henry, this is one of the reasons why it is now. There's another reason, is because remember, as the water is sucked out of the geyser, right? What happens inside that geyser? There becomes a negative pressure. And as there's a negative pressure, what's going to happen? And especially you find this on copper geysers, is the cylinder is now going to start collapsing in on itself. Because you need to, like for instance, if you take a Coke bottle, or not a Coke bottle, a plastic bottle, and you suck on it, what's going to happen? That's the water coming out of the system, then that whole system is going to collapse on you. So that's another reason why. But anyway, Herman, carry on there.
Okay. I thought you've explained everything already.
No, but this, I want you to just explain this specific one again with the specific drawing that you're showing, yeah. So you can just explain it with your...
Yeah, the vacuum breaker on the hot side, there's a hot water tap going out there. So it is possible for, if I understand the question correctly, I mean, let's ignore which the vacuum breaker at the top. If there's no if this vacuum breaker is not there, for instance, and maybe not even that one, okay. If there's a tap open on this side, on the other side, the inlet side of the geyser, water can run out in that direction, okay, which means it can suck the water through, and it can suck water up the spout of the tap and back into the geyser, okay. And it is important that the complete system must be protected from contamination. Not only the cold water. We make the assumption that only cold water can be consumed, but hot water must also remain protected. You don't know what materials could be potentially sucked up that pipe, for instance. The same applies not only in this scenario, but if the geyser is the highest point, exactly the same principle can happen. And if the air is not let in, water can be sucked from the wrong side into the geyser as well. Does that answer the question?
Yeah.
I think if I understand it correctly, the more important part is not how does the water get in there. Is it necessary to protect the hot water as well? And the answer is yes. It definitely is necessary to protect the hot water, because you do not know what type of contamination might find its way in there. I might be filling as I'm doing now, trying to get my swimming pool back to life, feeding it with all sorts of chemicals and having to top up everything. And if that situation happens, that nasty chemicals can end up in your bath, and you develop all sorts of nasty effects. Let me leave it at that.
Yeah, great. I hope that we answered that one. Just, Henry, just go away with it. Think about it. Apply your mind. And if you've got any other questions, come back next week. And when we do a recap, if you're still struggling with it, maybe we can just recap on it again next week. But just go and apply the mind and think. And just think about from the point of view also that when you suck on a plastic bottle, say the water is being drained out in a negative pressure, as it goes out, that bottle now starts collapsing in on itself. So that's one of the other reasons why. Good, great. Richard did just make a comment there, but I think it was picked up. Thanks, Richard. So I'm not going to repeat that specific comment there. With that, I think everybody is A-okay. I do apologize again, guys, for tonight's lateness. I do apologize for that from both our sides, but I'm sure the boss man will apologize now as well while he wraps up.
Yeah, do I have much of a choice? But okay, no, thanks for that, Lee. Yes, no, I really apologize for the challenges that we experienced in getting going this evening. Thank you very much for bearing with us. I see we went quite far over the time that we've set for ourselves. So I'm glad to have spent the time with you. Now let's see each other again in a week's time when we handle, and I forgot which one it is to handle. I think it's the pressure valves.
The safety valve.
Safety valve in the next section.
The most important thing of the whole system.
So,
yes.
Well, we can argue which one is the most important, but it definitely plays a very important role.
Yeah, I think so.
So everybody, I hope you have a good evening. Thank you very much.
Right, thank you very much. And then thank you very much to HeatTech again for sponsoring the course. It's highly appreciated. And guys, there is a survey afterwards, and remember the assessments. They will be up in a day or two, and the recordings as well. They'll be in the next day or two. Thank you very much, guys, and enjoy the rest of your evening. Thank you. Bye.